When 15 supernovae go off close together, both in time and proximity, it makes quite a bang. It should be of no surprise that such a violent event should fundamentally transform the region of space around where it occurred. Interstellar dust was swept aside from the forces of those concurrent blasts, creating a monumental void of low-density matter, and a shockwave that continues to hurtle across the galaxy to this day at a rate of 6 kilometers a second. In its wake, plasma, reaching 1 million degrees Celsius in temperature. This simultaneous Swiss cheesing and heating up of the interstellar medium is what is now called a hot bubble and represents both the end of stars and their beginning. But this is not some distant structure that lurks in a faraway corner of the universe. Our solar system isn't even heading right towards it. We're in it, charging for its point of origin head first. Welcome to our local hot bubble. What scientists now realize is the local environment that exists around our solar system. It's a neighborhood we are still exploring, but its nature is becoming clearer and clearer. So what do we know about the local hot bubble? How did it form? And what more is there to be discovered? I'm Alex McColgan, and you're watching Astrum. Join with me today as we walk in the aftermath of exploding stars and discuss how scientists even determined we were in the heart of a cataclysm to begin with. The local hot bubble was not always something we knew about. First identified in the 1970s from observations of low-energy X-ray emissions that were detected over the entire sky, the local hot bubble was hypothesized to be a large cavity in the interstellar medium called a superbubble filled with tenuous million-degree low-density gas. In the 1990s, scientists found that X-ray emissions could happen anywhere that neutral atoms interacted with the solar wind, challenging the idea that the emissions must point to a large hot bubble. But soon, evidence would reveal that the hypothesis from decades earlier was indeed correct. In 2014, NASA confirmed the existence of the LHB through the diffuse X-ray emission from the Local Galaxy mission, also known as DXL. While soft background radiation can come from other sources, like from comets, for example, the mission found that only 40% of the fog of low-energy X-rays came from within our solar system. This affirmed that the dominant source was diffuse X-ray emissions emanating from the million-degree region of interstellar plasma known as the LHB. Although this confirmed the bubble, questions remained about what could create such a massive void and what might explain the thousands of surrounding young stars. The prevailing answer proved to be both violent and fascinating. Recent research suggests that the local hot bubble was the aftermath of around 15 supernova explosions that occurred sequentially within a span of a few million years, erupting in relatively close proximity to one another. Scientists estimated that the first of these massive stellar explosions went off roughly 14 million years ago, each expelling enormous amounts of energy, pushing out the surrounding interstellar material and heating the remaining gas to extreme temperatures. Evidence of these ancient explosions has been preserved in our Earth's geological record in deep-sea sediment deposits, in the form of a special isotope called iron-60. This radioactive isotope can come from a few different sources, but the most common source of iron-60 is believed to be supernova explosions. We know that the source of the isotope is extraterrestrial because the Earth itself has no way of producing iron-60 on its own, and matching deposits have been found on the Moon as well. The reason that this radioactive isotope is special is because we know how long its half-life is, and we know that it decays into cobalt-60, another radioactive isotope, before it finally decays into nickel-60, a stable element. Iron-60 has a half-life of 2.6 million years, and cobalt-60 has a fairly short half-life of just 5.3 years. Because of this, when we find a deposit that contains these elements, scientists can compare the amounts of iron-60, cobalt-60 and nickel-60 like an elemental clock to reveal when that material was deposited on our planet. And lucky for us, international research teams have found several such deposits over the last couple of decades. In 2016, iron-60 deposits were found in deep-sea crust samples taken from the Pacific, Indian and Atlantic Oceans, indicating two distinct spikes in the radioactive debris that pointed to several supernova events in the not-so-distant past and not too far from our solar system, just 326 light-years away. The sample showed a spike of iron-60 between 3.2 and 1.7 million years ago, and another spike between 6.5 and 8.7 million years ago. Nuclear physicist Anton Wallner, who led one of these research teams studying the deposits, said that the fact that the more recent debris was spread across 1.5 million years suggests that there were a series of supernovae that occurred one after another in close succession. Astrophysicist Dieter Breichwert, who led a second team of scientists, identified a likely source of these supernova explosions, which would have occurred 196 to 423 light-years from the Sun. These supernovas that created our local hot bubble may have been part of an aging star cluster whose surviving members are now associated with the Scorpius-Centaurus stellar group. Using the iron-60 deposits, the team was able to trace the signals of two supernovas, one that happened 1.5 million years ago and the other 2.3 million years ago, as the result of the deaths of stars that were 8.8 times and 9.2 times the mass of our Sun, respectively. In fact, our LHB is still growing today, albeit much more slowly than when the supernovas exploded millions of years ago. The speed of expansion has plateaued at about 6 kilometers per second now, according to astrophysicist Catherine Zucker. In 2022, Zucker authored a groundbreaking paper that reconstructed the evolution of our galactic neighborhood, tracing the chain of events that created our local hot bubble and led to the formation of all of the young stars we see nearby today. From there, they made an incredible discovery. Using data from the European Space Agency's Gaia telescope, Zucker and her team were able to construct a 3D space-time map, showing that within 500 light-years of our planet, all of the young stars and star-forming regions reside on the surface of our local hot bubble. With these 3D positions and the 3D motions of the stellar clusters, they traced back 20 million years of star formation history near our local hot bubble. The implications were clear, that all of the well-known star-forming regions near our solar system had formed along the outer edge of the local bubble as it swept up gas during its expansion. Stellar nurseries are a field we're learning more about all the time, particularly as new images are taken by our telescopes. Here's a spectacular image of the Chameleon-1 dark cloud, one of our nearest stellar nurseries, taken by a dark-energy camera on the Victor M. Blanco 4-meter telescope at Cerro Tololo Inter-American Observatory. By studying the propagation of starlight from within it, scientists can tease out details about how stars form, which can help us better understand the local hot bubble's impact on our galaxy today. You might not have seen this particular image before, as new space news is coming out all the time. But I've talked about it in my newsletter, which I've recently launched to help you keep up with all the breathtaking photos released by our many telescopes on Earth and in orbit, or new breakthroughs that reshape how we understand the cosmos. You should sign up to never miss the most exciting news, even if the headlines do, by following the link in the description below. There are new editions that come out every Thursday. From the local hot bubble's birth 14 million years ago, Zucker and her colleagues identified 4 epochs of star formation on the bubble's shell. Starting about 16 million years ago, we see the birth of the Upper Centaurus Lupus or UCL star cluster, followed by the Lower Centaurus Crux or LCC star cluster. These formed about 49 light-years apart from one another, and about 14 million years ago these stellar populations were the source of the stars that went supernova to create our local bubble. About 10 million years ago, we see the first of the 4 star-forming epochs after the formation of the LHB, the Upper Scorpius Association, and older Ophiuchus stellar populations are born in this first epoch. 6 million years ago, the second star-forming epoch formed Corona Australis and the older stars of Taurus. Then around 2 million years ago, the stars in Lupus and Chameleon, as well as younger stellar populations of Taurus and Ophiuchus, came to be in the third epoch. And finally, our present time falls within the 4th star-forming epoch. We can observe the dense star-forming molecular gas that surrounds the LHB, which will eventually lead to more star clusters being born along the bubble's outer edge. With all of this stellar creation, you might be surprised to learn that we are interlopers. Our Sun did not form inside the local bubble. In fact, the Sun was about 978 light-years away when the first supernova went off in UCL and LCC, only joining up with the LHB about 5 million years ago as its path through this galaxy took it into the bubble. With the trajectory shown in yellow dots, you can see our Sun's location just before it entered the local bubble. And now, just by coincidence, our Sun happens to be located near the center of the LHB. Drifting into the heart of what was once a raging furnace, scientists became interested in mapping out the ongoing temperature within the local bubble. You might wonder why we're so calm if temperatures of plasma here can reach 1 million degrees. The key lies in that plasma's density. Look, this 3D map from Zucker's 2022 publication shows our local hot bubble in dark blue. The density inside our bubble is extraordinarily low, containing about 100 times less hydrogen than the typical interstellar medium. So while the temperature of this gas soars to around 1 million degrees Kelvin, giving rise to the diffuse X-ray emissions we have observed around the whole sky, we don't have much to worry about. Tracking temperatures within the local bubble has provided more evidence of its existence. The extended Röntgen survey with an imaging telescope array, better known as the Epochs X-ray telescope, has been able to gather the most detailed all-sky survey of soft X-rays to date, and that data has been used to map the LHB and our solar neighborhood in even more detail than before. Launched aboard the joint Russian and German mission Spectrum Röntgen Gamma, or Spectre-RG, in 2019, data from the Epochs X-ray telescope has allowed a team of scientists led by the Max Planck Institute for Extraterrestrial Physics to create a 3D map of the LHB and identify a temperature gradient where the galactic south was slightly hotter than the galactic north. This temperature dichotomy could be explained by supernova explosions in the past few million years, and by creating this bubble map, the team also found that the LHB is stretched out toward the poles of the galactic hemisphere. This is because the hot gas in the bubble expands out in the direction with the least resistance, which happens to be away from the Milky Way's galactic disk. Along with identifying temperature variations and the shape of the bubble, the team compiled this and other data to create an even more detailed map of our galactic neighborhood. In the new 3D map, our local hot bubble looks like a three-dimensional blue, white, yellow, and red splatter surrounded by and even overlapping other galactic structures. These other structures represent known supernova remnants like the Gum Nebula shown here in red. Other superbubbles, such as the one shown here in pale blue called GSH 238+00+09, and dense molecular clouds, shown here in orange. With the new data and 3D maps, these superbubbles seem likely to be common in our galaxy, creating a Milky Way that's sort of like Swiss cheese. The cavities of our Swiss cheese galaxy are blasted out by gigantic supernova explosions, with new stars forming along the edges of the holes created by dying stars. And like Swiss cheese, it appears that some of these superbubbles may have tunnels connecting them to other bubbles or other structures, suggesting our local hot bubble could be part of an intricate network of similar features throughout our galaxy. For example, we have the Canis Majoris tunnel, which lies on the Milky Way's galactic disk and is believed to connect our local hot bubble to the Gum Nebula, or another larger nearby superbubble. But the new 3D map also revealed another previously unknown interstellar tunnel, stretching towards the constellation Centaurus, possibly connecting our local bubble to the neighboring Loop 1 superbubble. While these interstellar tunnels are tantalizing, our current understanding of them is limited. Nevertheless, these tunnels of hot gas and bubbles of star formation, shaped by the death of gigantic older stars, has me in awe of how powerful and interconnected the evolution of our local galactic neighborhood really is. It suggests that stars are not just born and die in isolation, but that their energetic output continues to mold the environment for millions of years after their demise. And as our observational tools become more sophisticated, we're beginning to uncover the extent of these hidden structures. Next time you look up at the night sky, you might remind yourself that we are surrounded by crazy patterns, just like our local bubble in the Milky Way that was carved out by ancient cataclysms, and that some of those stars you see are actually plastered along the walls of a supernova-blasted cavity, which connects to other parts of the galaxy through interstellar tunnels.